All right, this is APAB Calculus. We're doing the Intro to BC unit, and this is topic number 4, Euler's method. Please say Euler, not Euler, because it is not Euler. So, to talk about Euler's method, we're going to first talk about what it does, and then we're going to talk about how it's actually a formula that you're really comfortable with. So, here's the idea behind Euler's method, right? So, the idea is that, let's say we want to approximate some curve, right? But we don't know anything except the differential equation for the curve and a starting value, right? So let's say we know that we have a starting value at, let's say, 1, 1, right? And knowing that starting value, we are and knowing the differential equation for the curve, we are able to approximate the line that would be tangential to the curve at that moment. Well, then we go some step away, like some delta x step away, and we use that curve. We follow that first line to the next spot, to that next delta x, right? And then, at that delta x, we use the same differential equation to say, oh, hey, I can approximate the tangent slope there, and I can follow it some step size later and use that to approximate a different point, right? And then we say, okay, cool, well now knowing that new point, I could find, using the differential equation, I could find the approximate tangent slope, and I could follow it some other delta x away, and then this would give me an approximation, right? So let's say I started at x is 1 and I wanted to end at x is 3, right? Well, I knew that f of 1 was 1, and I can approximate that f of 3 is approximately whatever y value this is, right? Like, I don't know, I'm just going to call this 7 for a fake number, right? So what we're doing is, it's called linear approximation because we're taking a curve that is not a line, and we are approximating it by using tangent lines. Now, there's a bunch of different linear approximation methods, but Euler's method is the one that we're going to learn here. Sometimes you'll also hear it called linearization because you're turning something into lines. So Euler's method is a linear approximation method. Now, one of the things I want to make really clear here is that Euler's method cannot sneak up on you. On an AP, they're going to have to use the words Euler's method, right? They're also going to have to tell you this step size, this delta x, and they're going to have to give you a starting value, and they're going to have to tell you what ending value they want, like f of 3 in this situation, right? So it can't be an accident. You can't be like, I wonder if this is an Euler's method problem, because it's going to say the words Euler's method. Just like you can't be like, I wonder if they want me to use a trapezoidal area approximation, because you know what it's going to say? Trapezoidal approximation, right? They're going to have to ask you for this specifically. So now let's talk as a second thing about what formula of a line we're going to use. So as we've talked about in Algebra 2 and Pre-Calc and APAB, the most convenient form of lines to use is generally point slope, right? So y minus the y value equals m x minus the x value, right? That's the easiest version of this to use. So when we talk about doing this, right, one way to think about it is we could pretend, and it's not really pretending, but we can think of x1, y1 as the given initial value, right? That's the numbers that we know, right? So if that's my initial value, then my new y would be equal to the old y, because I'll add that y1 over, plus the slope times, and then this is an interesting thing, the amount of x difference from the first x to the next x, that's called delta x. So we can find the slope by using the differential equation. We're going to be given some delta x, and we're going to use these quantities, so the given y, the slope that we can find with dy dx, and the given delta x to find a new y. We're then going to repeat the same step, but the new y and the new x will become the y and x that we use in the formula, right? And so on. So let's walk through how this works. I do my Euler's method as a table. You don't have to do yours as a table, but I am not an organized human by nature, so the way I do my Euler's method is like this. I make a column for my x's, I make a column for my y's, I write what my slope is, which is my dy dx formula, whatever I'm given, and then I go ahead and write my point slope. Y new equals y old plus the slope times delta x. And then every time I fill out a row, right, every time I find a new y, it goes back in this spot, and then I keep going. So this is the way I do Euler's method. Again, lots of different people are going to show you different ways. Most of the time, at most, you're going to be asked to do 2 rounds of Euler's method. Meaning, if you're given the first 2 points, you're going to have to do it once, you're going to have to do it twice, and your answer is going to be right here. The most is sometimes you'll have a textbook that asks you to do a lot of times with the aid of a calculator, which is just mean. So let's go ahead and walk through an Euler's question. We're going to go ahead and do example 1. So in example 1, we're given that the starting point is f of 1 is 3. We are given that dy dx is a 2x minus y. And we are asked to use 2 steps. That's not how you spell steps. To get the approximate value for f of 2. Okay, so here they didn't tell you the step size, but they did tell you to use 2 equal steps. So you do have to do a little bit of math here. You're going from 1 to 2 in 2 equal steps. So your delta x is going to be the ending value, 2, minus the starting value, divided by the number of steps, meaning you're going to be using steps of 0.5. So when I fill out my table, here's what I do. I put my starting value, 1, 3, as the original value in the row. I also know that my step size is 1.5, so I should be going from 1 to 1.5 and from 1.5 to 2, meaning that this value right here, when I get to it in my table, that's going to be my answer, right? Like this is going to be the answer right here if I can get to that y value. That's my approximation. So to find my slope, I'm going to use dy dx equals 2x minus y, right? So my slope in the first row is going to be 2x, which would be 2, minus y, which is 3, so I get a slope of -1. I now use that -1 slope and say, cool, my new y value should be the old y, which was 3, plus a -1 times a 0.5. Well, that's 3 plus a -0.5. That's a 2.5. Or if you like 5 halves better, that's fine too. I then use these 2 values to get my new slope, right? My new slope is going to end up being 2 times the 1.5, right? 2 times 1.5, because that's 2x, minus the y, which is 2.5. So that's 3 minus 2.5, so that means my new slope is 8.5. So then my y new, which is going to end up being my final answer, is the old y, 2.5, plus the slope, 0.5 times 0.5. Well, that is a 2.5 plus a 0.25. Sorry, on the sheet I accidentally had as a minus. So that is a 2.75, and that's my final answer. So my f of 2, right, so my answer in this problem is that f of 2 is approximately a 2.75, right? So again, they're going to tell you how many steps to use, or they're going to tell you the step size, or both, right? You're going to have the x and the y, use them to find slope, and then use point slope formula to find the new y. Do it again, do it again, do it again. When they give you this on an AP, they generally give you 2 points, one for the correct answer and one for doing however many rounds of Euler's you were supposed to do. Meaning, they get that sometimes the addition's going to go wrong and that you're going to be super bummed and this answer. So for instance, on my original copy of this worksheet that I totally wrote, I accidentally put a minus here. I have no good reason why, but I did. I'm guessing it's because I copied this equation to here and then just forgot to get rid of the negative, so I had this answer wrong but had done all the work right. That would be worth 1 of the 2 points on an AP. Usually Euler's is worth 2 points.